Hi everyone, Shomik here. As the title suggests, what I will tell you a little bit regarding is random circuit sampling with non-unital noise. This work is a collaboration with Bill, Kodai, Michael, and Kunal. They're all here, so feel free to talk to them later regarding this work. Okay, so the starting point of this talk is the observation that random circuits have been a very popular platform to try and demonstrate that quantum computers beat classical ones in sampling tasks. So, how valid are these claims? Well, there are two perspectives to this. One is the theoretical perspective. And for theory, we have a long line of research that strongly suggests that, at least for the noiseless case, random circuit sampling does give you quantum speed up over classical. However, there's another perspective to this work, and that's from hardware, like practical demonstrations. So, all practical demonstrations, all practical hardware, they will have noise. But even then, there has been claims of quantum speed up. For instance, Google's very recent 67 qubit random circuit sampling demonstration, that was noisy. Uh, there have been claims that even with noise, these demonstrations have achieved something that's just beyond the scope of state of the art classical simulators that we know right now. But the caveat, once again, is that these demonstrations are noisy. And when you have noise and you don't correct for the noise, then as the system size grows, it's very plausible to expect that the quantum signal dies down. So, this leads us to a very natural question, that of whether we can get any quantum speed up with noisy quantum circuits in the asymptotic limit when the system size is large enough. So, this is our result, our main result. We show that for realistic noise models, when we are trying to faithfully model what's happening in real hardware, for those models, all current techniques to show hardness or lack thereof for tasks like noisy random circuit sampling, these break down. And we need new, like the tools that we need, like the, like, and we need new tools to tackle this question. Now let's loop back a little bit. Let's try to recap what we know about noise and these quantum advantage demonstrations. Well, the starting question here is how we model noise. Well, before us, most previous work modeled noise as depolarizing. What is depolarizing noise? It's given by this CPTP map, where P here is the noise strength and P is a constant. As you can see, the fixed point of this map is the maximally mixed state. So, what's the actual model of our circuit, the one that we consider? It's something like this. We start from, say, 0 to the n, the starting state. Now we have a quantum circuit. These white rectangles are random gates, and these red dots, these are noise channels. So, the question that we started from, could we squeeze out any quantum speed up from circuits like this? Well, like I said, the fixed point of this channel, this noise channel, is the maximally mixed state. When you measure the maximally mixed state in the standard basis, you get the flat distribution. So, in this sense, what this noise does is that it takes you to a high entropy state, and such that when you measure, you get a very flat distribution that's trivial to sample from. And this convergence to something flat, this flatness property, this gets worse and worse with depth. So for high depth, say super logarithmic depth or higher, classically sampling from this distribution is trivial. You just flip a bunch of fair coins and that suffices. There was a paper in the Belgium QIP, which many of you have seen probably, by Dorit and collaborators, which said that this classical easiness of sampling, this persists at logarithmic depth as well by slightly sophisticated techniques, but the main point is still this flatness property that the distribution has because of this noise. However, the interesting point to note here is that the complexity of this task is unknown for sublogarithmic depths. Why is that so? Anti-concentration, which is the formal fancy name for this flatness property that I keep talking about, this fails for sublogarithmic depth. And anti-concentration is a key ingredient in all easiness and hardness proofs of random circuit sampling, the ones that we know so far. And because this flatness property fails, we do not know how to tackle this question for sublogarithmic depths. Just to tease the rest of the talk, what we will show is that the same phenomena, morally the same phenomena, is true for other noise models and depth regimes. Why should we consider a different noise model? Why doesn't depolarizing suffice? Well, it's just because nature isn't just depolarizing. Modeling the entirety of noise that's present in the system as depolarizing is very reductive. Like real world noise is slightly more complicated. So, how should we model realistic noise? What's a better model than what we just saw? Well, you could broadly categorize realistic noise into two types. Unital noise is one type. I call these depolarizing type noises. Why? Because the behavior is very similar to depolarizing. It takes you to a high entropy state. So it's like the output distribution when you measure in the standard basis is like more flat or more scrambling. However, there's another very important type of noise present in nature, non-unital noise. And this type of noise can potentially take you to a low entropy state. So like less flatness or less scrambling of the distribution. And at the very least, when we are trying to model realistic noise, that noise model should have at least these two components. But now we have a tussle. The unital noise tends to scramble the distribution. And non-unital noise potentially tries to do something completely different. So in this sense, there's a fight between these two noise sources. And you could ask, who wins this fight? Our result, to state informally, says non-unital noise is the victor. It wins this fight. So the output distribution of circuits with both types of noises present will never look flat. It will never have the flatness property. So how do we model non-unital noise? Well, one popular way to do this is to model it by some sort of a damping noise. This is a good model, for instance, of what goes on in hardware in the form of, say, T1 decay or readout bias. So what is this damping noise? Amplitude damping, for instance, can be represented by a Stein spring-like representation in the following way. Say I have noise strength P The noise takes 0 to 0, but for 1, it takes it to a combination of 0 and 1. But the first register, that's the system register. As you can see, the property of this type of a noise is to bias the system towards the 0 state. And if you squint hard at this noise model, what you'll see that is that the fixed point of this noise is the state 0. So it tries to take the system towards this state, and as you can see, this is a low entropy state. So it tends to take the system towards a low entropy state. And our results in the paper that works for a wide variety of non-unital noise models. This is one of them. This is popular, but this is just for demonstration. The results are fairly general. So what's our circuit again, to recap? It's the same circuit that you saw before. Now there are these blue dots, apart from the red dots. These blue dots are non-unital noise sources, and the red dots are still depolarizing. And the position of these dots do not matter. The same results hold when you flip the position. And we still measure in the standard basis in the end. So what's our formal result? We say that this flatness property never holds for the type of circuit that we just saw. Anti-concentration is not satisfied for these circuits. And this is true at any depth. And this is true even in the presence of any depolarizing type noise in the system. And this is true for any relative strength of the two noises. So for instance, the depolarizing type noise, say that has very high strength, like 0.99 for instance, and say the damping part is like 0.001 for instance. Even then this result is true. Anti-concentration is not satisfied. So all known hardness results and classical simulability results for random circuits of this form, these break down, because they all rely on this flatness property. So what does our result say about quantum speed-up demonstrations with noisy random circuits? It says that we do not understand the complexity of this question, and our current techniques are not sufficient to tackle this question. We need new techniques, both for proving hardness and for proving classical simulability. So how do we define this flatness property? Well, the high-level picture, the qualitative picture, is that this property indicates that the output probabilities of the distribution, when you measure in the standard basis, that's like sufficiently high. The probability mass is sufficiently spread out. So more mathematically, say B is a collection of quantum circuits, and say I take a typical circuit from B. Then for that circuit, for all choices of bit strings X, the probability mass on X is sufficiently large. That's what this says. Well, now let's look at some of the techniques that we have to prove the result. So one sufficient way to violate this definition that we just saw in the last slide is to prove something like this, which we prove is indeed true for noisy random circuits of the form we are talking about. So what's this statement? Let's parse this. So this says that say B is once again a collection of random quantum circuits with both types of noises present. And say I take a typical circuit from B. So for that circuit, the probability mass on strings with high Hamming weight will be extremely tiny. And if you stare at this equation here, then this is sufficient to violate the condition that we just saw. So the output distribution, if we can prove this, this will not satisfy the flatness property we mathematically described. And how do we prove this? Well, we do it by a very standard technique. We compute the first moment, we compute the second moment, and then we apply a very standard second moment bound, like a Chebyshev. So how do we compute the first and the second moments? Well, one easy way in which we do some of the calculations, for instance, computing the second moment or lower bounding the, computing the first moment and lower bounding the second moment, is something like this. We take the circuit, then we separate it out into a last layer of noise and the rest of the circuit. So N and C prime. And then we take the adjoint of the noise operator, bring it to the front like this, and then we use properties of the noise to compute exactly the first moment and lower bound the second moment. So why do we care about lower bounding the second moment? Anti-concentration, for those of you who are familiar with the literature, has been defined in many ways. One definition is what we just saw. There's another definition in terms of collision probabilities. Like a collision probability is trying to measure, say we sample repeatedly from the distribution if we get collisions. For a flat distribution where the mass is sufficiently well spread, the number of collisions will be really tiny. We show that this is not the case. So the second moment directly corresponds to the collision probability. And we show that the second moment, by giving a lower bound, we show that it's sufficiently large. So the number of collisions is not tiny. And it violates this second definition of this phenomena. And to upper bound the second moment so that we can apply a Chebyshev type relation, it's slightly more technical. Let me briefly sketch out the steps here. So we have two main tools here. The first is mapping the circuit to a statistical mechanical partition function, and then doing some simplifications. For instance, replacing every 2-qubit gate with two 1-qubit gates. These are standard techniques that have been studied before to talk about random circuits. The novelty here is that we design versions of these techniques that are robust to non-unital noise. And once we have this, we just apply a Chebyshev. So in summary, so what's next for random circuit sampling? Now that we have seen this result. Well, the way I see it, there are two main questions. What are they? The first is asymptotic hardness. We have seen this realistic noise model, and we have talked about random circuit sampling as a task. So what is the complexity of this task? Could we design better techniques robust to these types of noises such that we can prove hardness for noisy random circuit sampling in this regime? The second question, which in my view is slightly disconnected from the first question, is classical simulability, but for finite system sizes. So complexity theory doesn't exactly let you argue about systems with finite sizes. So this is a different type of a question in that regard. What would this say? This is asking, say for the demonstrations we have now, for which quantum speedups have been claimed, demonstrations which have both depolarizing and damping type noises present. For instance, Google's 67-qubit demonstration. Are they beyond the reach of classical samplers? Or could we design better samplers that spoof these demonstrations? So in conclusion, realistic noise is quite complicated, as we have discussed. We don't understand it too well. And how powerful is noisy random circuit sampling? Well, we don't know. This is an unresolved question. Anti concentration fails. Current techniques to deal with this question rely on that phenomena. So, that failing means we need new techniques to argue about both hardness and classical simulability. So, in an upcoming work, which we haven't posted yet, we show that uh, a different question can be tackled. The question of calculating mean values of certain Hamiltonians with these noisy random circuits. These remain easy with respect to like a choice of precision and depth. Uh, this is poster 487 today if you want to check it out. However, the very important caveat here uh, is that this is nothing about the complexity of sampling from these circuits. The complexity of random circuit sampling with these types of noise models is still an like a, that is still something that we do not know. That question has not been resolved.
Okay. Um, any questions? You can maybe step up to the mic over here, please.
Hi. I have a kind of specific technical question. So you mentioned that you do an analysis where every 2-qubit gate becomes two 1-qubit gates. So does that mean in your analysis you're analyzing a circuit composed of 1-qubit gates?
Yeah, like many copies of, let's say, like 1 qubit gates. Like the way we bound the second moment is first we consider, like, let's say, this simplification, then bound the second moment of this modified circuit with, let's say, like the second moment of this, like the thing that we started with, and then talk about, let's say, the second moment for this modified
Oh, it's
circuit.
like it's a bound.
Yeah, yeah,
I
yeah.
see.
Yeah, it's a bound.
I
Yeah.
see. Thanks.
More questions?
Thanks for the great talk. Could you comment on the last point on your previous slide about the local observable, like you're computing the mean of the observables? I was wondering, like, why do we expect the mean, like computing the mean to be hard? I would have thought like computing higher moments of the observables would have been harder. So
Right, that's a great question. Yeah, so there's no reason per se to say that computing. There's no relation between classically sampling from these distributions and computing mean values. These are like two separate questions, and that was the point of having that bullet, to stress on the fact that these things are quite separate. Like one doesn't mean the second.
Okay, thank you for talk. I was wondering if the results of your work has any implications on the trainability of, let's say, variational algorithms or the Baron-Plateau problem.
Yeah, so check out poster 487 for that, where we prove that if we have non-unital noise and random circuits, we do not have barren plateaus.
Okay. Okay.
And does that mean that that gives us like a speed up, like for variational procedures? That's not clear. But like we do not have barren plateaus. That can be proven.
Okay, but the trainability is still like a.
There's a fine print there. Like
Okay.
what? Check out poster 487.
Okay. Okay. Thank you.
Okay. How about one more question?
Hello? Yeah, yeah, somehow you said that these anti-constant, like if you can show that the circuit is like becomes flat, it's been used to demonstrate both
Yes.
the hardness results and simulability results. Like somehow simulability results, it seems like, okay, maybe, okay, it all looks random. You can, is there some intuition for why this phenomenon can also be used to show hardness?
Yeah, that's a great question. Let me try to give the qualitative high level picture. So this flatness property, say the distribution is catastrophically flat. So it's like maximally flat. Then it's like trivial to sample from this, right? Like just flip a bunch of random coins. But why is it hard? Yeah, so one crude way of thinking about this is for all these quantum speed up demonstrations with random circuits, the starting point in some sense, to design these things, is to start from, let's say, like think about hard random states and then try to mimic properties of hard random states. Well, one property, like hard random states are hard to like say like classically simulate. So one property of hard random states is when you measure the state in the standard basis, the distribution that you have has a Porter Thomas type property. So what's that? That means it satisfies this flatness property, uh, but it's also like not maximally or catastrophically flat. Like there's a Goldilocks zone of flatness that these like hard to simulate states have, and what these demonstrations are trying to get at is trying to design like a poor man's version of these types of states. And so that's where like that's why uh, hardness results so far leverage this property. The fact that the main thing is trying to mimic hard random states and like properties of that.
Okay, thank you.
Okay, let's thank the speaker again.